Hi, my name is Matthew Hershey, and this is my MAE 535 demo project. Today I will demonstrate inductive AC wireless power transmission. This demonstration will seek to show in practice the principle known as Faraday's law of induction. That law states that a time-varying magnetic flux linkage cutting across a conductor induces electric current. And that's also known as speed voltage or back EMF. So this induced voltage is defined as the negative of the time rate of change of the flux linkage across the conductor. Magnetic flux linkage, lambda, is equal to the product of the number of coils N times the magnetic flux phi. In turn, magnetic flux phi is a product of magnetic flux density B and the area enclosed by the coil. Magnetic flux density is defined if we assume a linear relationship between it and the magnetic field due to air being the medium. It is the product of the permeability of free space times a magnetic field. And that magnetic field, based on Ampere's law for a coil, can be defined as the number of coils times the current in those coils divided by the axial length. And ultimately, the induced voltage is found to be a product of several constant terms times the time rate of change of current in the coil. These constant terms can be used to define inductance L, which is the number of coils squared times the permeability of free space times the area within the coils divided by the axial length of those coils. So voltage induced is equal to the negative of inductance times the time rate of change of current. Knowing this, in this demonstration, we'll construct two circuits that each have an inductor, and that inductor will be made of a 200 loop coil of insulated wire of a radius of 5 centimeters and an axial length of 1.8 centimeters. Now, knowing these parameters, we can calculate the inductance of each of these elements, and so each of these identical inductors will have an inductance of approximately 2.19 times 10 to the minus 2 henries. You see an overview of the device comprised of two independent circuits and a schematic for those two independent circuits. On the one hand, you have what we calling the active circuit, which is powered by an AC source on the right-hand side, and it includes resistors, a switch, and an inductor, again of the 200 loop coil. On the left-hand side, you see the passive circuit, not electrically or wired in any way to the active circuit, and the passive circuit contains an inductor, a full-wave bridge rectifier, capacitor, an LED, and resistors. And then a voltmeter is used to measure the voltage across the capacitor. Just as the diagram showed earlier, two circuits independent of one another. On the left-hand side, what we call the passive circuit, and on the right side, the active. The one on the left-hand side is the one to be powered through inductance, and the one on the right-hand side is the one hooked up to an AC power supply, basically a transformer supplying about approximately 16 AC volts. On the left-hand side, we see a multimeter measuring voltage that's connected on both sides of the capacitor, and you can see now that it's measuring 0 volts. And just to demonstrate the principle, this is not the main demo, but just a small, quick device to make. Just a single coil of 200 loops with the permanent magnet inside. You can see the time-varying magnetic flux will generate power, and shows an LED lighting up there. But moving on to the power transmission device, we go ahead and flip the switch to power the active side. Of course, still see no power transmitted yet, but then coupling the two inductors and kind of jiggling the jostling the switch a little bit, which makes the circuit kind of connect at a slightly different frequency. It could be that it's too quick, and the way we got it to work, was using this method. But now we see voltage climbing and the LED, though faint, lighting up periodically. About 5 volts and now about 6.5. So we see clearly energy being transmitted from this active side, the right-hand side, to the left-hand side through the inductance.